Second speaker is Lukasz Stettner. Maybe I only translate Polish Academy of Sciences and the title.
Okay, so first of all, I'd like to thank the organizers for a very nice meeting. And I'm going to talk about one of the major problems that my field arises in engineering sciences, namely the problem of partial observation. And the problem I'm going to study is as follows. Positively, I assume that I have in Markov process Xn with transition operator Pun Xn at the very time n, this initial load Q. And then I do not observe this process, I get only partial observation. And my partial observation is of this form. This is a function h of Xn, and this is h is arbitrary function, so it may happen that it is not one-to-one function, because otherwise I would have a complete observation, but this is not the case. And then my control, which is choosing, which has an influence of the transition operator, is adapted to sigma p generated by my observations of process y0, yn. And my strategy will be a process which will be adapted to this. It will be evaluated, it will take a value in a compact metric space. So, first, what I'm going to study is to study such a cost function. So, this is average running reward per unit time. So, we have cost function in process starts with mu, and then we have sum up to from I to 0 up to -1. I should assume that the C is bounded running cost and is 1 over n. So this is my running cost. And such problem, for a long time, it was an open problem to study in this setting. And in a sense, first positive result, solution to this problem, was given in my paper in 1993, and then this was extended by Borka, and with the paper, and then there was a mistake correction note, and then the most general paper is by Arab studies and his collaborators. But this was an additive noise, so this was the case when to this HXN was added an additive noise. But here I have one extreme point, because it's a case, because I don't have this additive noise. And why this additive noise is very convenient? Because then we can use so-called the reference probability method. In a sense, we can change measure. We can introduce new measure under which this process Yn, we have an additive noise. This process Yn will be sequence of IID random variables. Xn will be a process with this transition operator, and then we will have it such that Yn will be independent under this measure of the process Xn up to Yn from process Xi with time up to n. So this was a major tool which was used, and this was in a sense a major restriction problem. So this the result I mentioned was based on this. What about the degenerate observation? So the observation I mentioned here. So the problem is rather old. Was stated by Lévy Blackwell in 1956. He was a very well-known statistician, and for him there was a conference in Lévy in 1957 when he posed this problem. And the problem, his problem was because here I actually intended because the usual process we described is so-called filtering process, and the question was what is the influence of this, what is the ergodic behavior of this filtering process under partial observation, when we have this kind of observation. And there is a sequence of papers by Kaiser, then Koopman and Ritz, Chigansky, Van Handel, and once again another paper by Kaiser, but all these papers concern finite state space, and then they studied the exigent condition for ergodicity of filtering processes. This problem was, in a sense, this paper by Kaiser was used to notice a mistake in the famous paper by Kunita from 1972, in which formulated sufficient condition for ergodicity of filtering process, and in fact this was his paper contained a mistake, and the counter-example of the mistake was based on the paper by Kaiser. I should formulate a control version of this counter-exam, and then there were improvement papers by Handel, but this concerns non-degenerate. This is actually in this case, both in continuous and in discrete case. And concerning degenerate observation, we get just a Markov chains in this time, we have the first paper of this form. Now, because I was asked also to not only to solve, but also to formulate the problem and to find a kind of connection between Poland and Mexico. So instead of cost function, which I call this additive cost function, because this ergodic, but we have additive cost function, we can consider multiplicative cost function. And we can sum. And then we can also might be interested to find an optimal strategy maximizing this cost function. But here the only result are concerned under reference probability method, and this is under the case when we have non-degenerate observation. This is considered additive noise, for example, and the paper is by Massive Massive, and independently the result was obtained by Daniel Fernandez. And in fact, there are no analog of the result I'm going to present here for the case of multiplicative cost function. Generally is that we have to problem to define the real state process, because state process here will not be a normalized measure value process. Here we have a problem with Markovianity. Okay, but now let me be a bit more concrete. So what I have a process xn, which is a control operator. I have initial view, and I assume that xn belongs to the state space, which is a Polish. Later on, generally I should consider this as a Polish, but later on you should see several restrictions I should have to assume about this, which in fact works as a state with this compact. And my observation is on this point. And first, how to solve this case? So first assume that, let's say something about observation space, and assume that when the observation space is countable. So then we can define that there is a finite sequence of sets AI such that this Hx is equal to AI. And my process we are looking for is filtering process of this form. This is a additional probability that xn belongs to B in my observation. And here in this setting, when this is countable, so we can write down an explicit formula for filtering process. Filtering process, this formula will be of this form. this operator n, un, it depends on pi n, and yn plus 1 is by observation. So one can see that this is summation, but in fact it depends on the value of this process y, because yn plus 1. And then in fact here we have only one term, because the other will be equal 0. But the term of this form. And then you can see that here is a problem that here of course we have this AI. We assume that this is non-negative, this is positive, so that it makes sense. If we assume that the T will be general, we'll have a problem. We won't have this form. And the result, which is consequence of this, is that this filtering process defined in this way is a Markov process. Also is in quotation mark, because Markov, in a sense, it depends on at time n of the process at time n plus 1 depends on the observation and on un. And transition operator can be written as a filtering process that depends on pi n and un, and transition to the next step to the pi n plus 1, and then we have the formula to calculate the formula. So it's a control to measure value process. And now, but the question is now, what will happen when D is not counted? So of course, if I denote by D0 the set of all spaces in observation space for each singleton, so we have filtering process is just an inversion of operator H, function H, and this is just a Dirac inversion. So this is just simple, but what if yn does not belong to this set D0? It should be D0. So then we have a problem. We have a problem with generally Markovianity. Because once we have a Markovianity, then there will be a problem of probabilistic and so on. So but when we assume a covering of the state space, sequence of coverings with diameter not greater than epsilon, and so we have such a, that for epsilon 1 less smaller than epsilon 2, because the covering epsilon 2 is contained in this. So then we can have this event that should be yn lowercase yn plus 1. And then we can define a semi-approximate filter process. And then one can see that letting epsilon to 0 as a limit, we obtain just a real filtering process with non-degenerate observation, pure no sure. So then this fact can be used for each epsilon. I can formulate, I have a formula for transition operator given transition in the previous step, and I get this form, and then what one can show that if I take f as a function measure, continuous function from the space of probability measures into R, then I can show that the conditional transition probabilities they converge to certain transition operator. So we can define the transition operator for a filtering process, and then we have that in general case this pi n process defined with our degenerate observation as a Markov process with a transition operator. So when we have a Markov process, of course, this is the first step. We can see about the ergodicity of this Markov process is such an observation. And now one important example of a controlled Markov process, just to show you that this is there are many problems, and that the situation is not so clear even because first intuition for a long time was such that if the state process is sufficiently ergodic, so that no matter what observation we have, our filtering process should be ergodic. But this is not true. And then for this case, consider such a very simple model when we have state space, Markov process with a finite state space. This transition operator depends on the control. This is for control equal 1 or 2. For equal 1, this is the transition operator, so this means that from the states at state A1 is probably 1/2, then moves to A2 is probably 1/2, and then it is in A2 it stays in this state, or is probably 1/2, or moves to the other, and then so this is a very nice ergodic process. But what is observation? Observation is such that I observe, there are two states. I observe when the process is in the state either E1 or E3, or E2, E4. I recognize only these two states, but I don't know if my observation is E1, I don't know whether this is E1 or in E3. And if my observation is equal 0, I don't know whether it's E2 or E4. And one can show that my observation, Y is a sequence of IABN variance, probably 1/2. And then we can just construct filtering process. And what appears that assuming that we choose control U1, because this is first for this U1, maybe for U2 I just, and then it depends on the value of Y, process Y. So if Y1 is equal to 1, so then the process enters, starting with initial low mu, the process enters this set. This probability measure is concentrated on the first and the second, and then in the third state, and this is just the values. And then the process either is probability 1/2 stays in this, or it moves to the next step, so it moves in there. When it stays is 1/2, and then it moves there, and the same here, and from here it stays 1/2, and it moves once again. Here. So in a sense, I have a set, in a sense I stay in this invariant set, and this set depends on my initial log. So one can easily see that, of course, it becomes observation Y1, but this is one invariant set. In this set, so my invariant measures equal 1/4 corresponding to each of these states, which are generated by initial log. And here, if the initial, my observation Y1 is equal to 0, so one can see that under control U1, this observation is such, so then I have the following state, different state here, then I move. So in a sense, depending whether Y1 is equal to 1 or Y1 is equal to 2, we enter one invariant set or the other invariant set. Of course, and there are two different invariant sets, and when I mean one invariant set, the invariant measure is just 1/4 in each of the states. So in a sense, given the state mu, this is a transient state, and I get a jump, and in the case of control U2, the situation is similar, but of course we start from this, so once again we have this, if U2 is Y1 is equal to 1, so we have this state. If it stays, so it changes the order between this problem, but or if it moves, so it moves to this set. And then still we have a fine number of states, a lot of states, and then we have this invariant set, and then in the other case we have different, but the also invariant set. Of course, they are different if this U1 is less not equal to 3, and U2 is not equal to 4. And we have two invariant sets, and we have the 1/4 measure. And then, of course, one can see another fact is that if we change the control, so we can change invariant measures, because if we can change the control, then So first here we see that the invariant sets under control U2 are the same as the invariances under U3, but it depends on the form of transitional operator. But using control, we can change a bit structure of the processes, and then we can see that starting from one process of this form, we can enter, we can change it, and we can, in a sense, summary is such that this state will be recurrent, but invariant measures with the control change, we can choose the control in a form of Markov control such that the organic structure will be different. It is not the case that this is uniformly distributed. But the result is such that if we, degenerate observation, we may have many invariant measures. And here was just associated with many invariant sets in such a simple case. But now let's come back to the control case. So in a sense, the output is such that in the control case, we cannot rely strongly on properties of embodied properties of filtering processes because they may not be guaranteed. So we are using different approach, and the general approach we are using is the historical approach, is the vanishing discount approach. In fact, this approach was first used in my paper, which I mentioned in 1993, and then in the other paper this was used. But I shall use this paper first to the case of countable observation state space, and then I'm going to show that even if the state space is not countable, this general state space, when I don't have explicit form for filtering process, but I have a transition operator, also I know as a limit transitional operator, but I don't have explicit form for this transition operator, it will appear that I can solve the problem. But the method I'm using is I'm solving first for the countable observation process, and this is so-called vanishing discount approach. So instead of this average cost per unit time problem, I consider discounted problem. Discounted problem, assuming that C is bounded, is continuous bounded function with respect to those coordinates. So the value function will be beta to this function is a solution to this relevant equation. In the sense that it's a contraction in the space of continuous bounded functions, where this phi is just the transition operator behind here is the assumption, and the assumption technically I shall only later on consideration under it is true that my transition operators for filtering process is continuous. So in a sense here we have space of new control parameter which is from a compact set, and new topology of new I consider that this is just a big controversial topology, although later on I shall meet the assumptions which require much stronger credibility. But here the result is such that for each beta there is a solution to the one equation which can be approximated uniformly. This is important because it will be used later on. Where it says the approximation by a function Vn. Then this is a convex function for each n. Here beta is a complex function. This is important, and of course the optimal control is just a select this equation put to the filtering process, so we have a complete solution to the discounted problem. Then, as usual, here we want to come back from discounted to process we subtract, we fix one value into this function W beta. When I consider the relevant equation I have now in this form, I get this is the formula for my filtering process in the case of countable observation space. But here a first assumption appears, which will be needed. It is such that certain infimum for given u of this, assuming a spread from Z1 and Z prime, this infimum should be strictly positive. So this is why I said that usually, because this is just operator, this transition operator should be in a sense equivalent. Not only it's a bit more than equivalent. And then this is the result that usually the state space is compact. But what is the result of this is such that if I consider these measure various process, this process will be measured. The value for any set P, but this will be not negative. And then using convexity property, I get this approximation. And then first, one result is that this is based on an adaptation of my former papers from 1993. The argument that under this A1, the span norm is means of beta subprimum minus infimum to the span norm, but with respect to beta, test for interval 0, 1, that for each is bounded, so it's uniformly bounded. And therefore this function that beta is uniformly bounded. It's a key argument, and then the other argument is kind of a continuity. I define function lambda mu continuity in this form. This is infimum. I assume that this is continuous. Continuity, this means that if mu converges mu and converges to mu and converges to mu, so this converges to 1. So this is a kind of continuity with respect to feedback law. In the sense that it's not feedback law, but it's more equivalent form. And then from discounted Bellman equation I have this, and then I have a certain approximation, and I can consider the difference because I would like to have that this is actually continuous. And for each I can estimate this value. This will be close for each beta, independently of beta, uniformly in beta. And then I'm using once again convexity arguments. So that all trick was based in my 1993 papers, and that was based on continuity, on convexity arguments, which is now adapted in a more smart way. And then using this, I can get the following estimation that for this beta, and then one can show that under these two assumptions, A1 and A2, this function v beta is continuous uniformly with respect to beta. So when I know that this function v beta is uniformly continuous, and I know that this is bounded, so I can choose a subsequence that it will converge. And then the main term in the countable observation is such that we have here, and I can let beta go to infinity, and the main result is such that there exists a gamma such that 1 over beta, the optimal cost for discounted, converges to gamma for every mu, and there exists an optimal, there exists a continuous bounded function which sits at the following Bellman equation. This gamma is just the optimal value of my cost function, and the strategy, this subprimum, selector of the subprimum is an optimal strategy. So the problem is solved for countable state space, but here I used the form of transition operator and also the form of filtering process. But what happens if I have we next consider general case without restriction on H. So we do not case that H has at most a countable number of values. This is general case. Then I need one more assumption, this A3, continuity of this operator. Once again, when the state space C is compact, so this is not a strong assumption, otherwise this is rather strong. And then, but under this, we have the following result. We have the transition operator. This is approximate, because now this is with epsilon. This is in the case when my filtering, my observation was limited to this covering with a radius not larger than epsilon. And when I just use only this observation, and then one can see that for each epsilon we have such a continuity of transition operator, and then we also have this for a limit operator under this assumption. This was important. And then the limit concerning, then we have just convergence, very strong convergence of transition operator concerning to the approximation of my filtering process using countable observation. And then we are working with, from a one hand side, we are working with Bellman equation corresponding to countable observation, and then we have a Bellman equation corresponding to discounted, corresponding to observation, to general observation. Lemma is the following. One can show that we have for each beta we have a uniform convergence. It's under assumption I assumed, and then further to continue I need proposition plan 1 and 2. I need a bit more detailed estimation, and I've got this estimation. I noted that this estimation here for a span norm does not depend on epsilon, on this covering. So I have a general estimation, and the same I have a general, so as a result I have also, assuming epsilon go to 0, because I know I have also the estimation for my discounted problem with general observation. And the other hand is result is concerning continuity of I have continuity with respect to of this with countable observation. I have once again I have here I have epsilon. I have the bound which does not depend on epsilon, and this is just a positive result when I have this lambda mu of this form, and therefore if I define in this, I can show that this will be bounded uniformly continuous. I have this approximation, and in fact I can just come to discounted Bellman equation, let beta go to 1, and then I have the result similar, but the result in general case. In the case when I don't have explicit form for filtering process, when I don't have explicit form for transition operator, but the process is well defined, and I have an optimal strategy. So the problem is completely solved, although under certain set of assumptions. And now what about other problems? The other problems is that I needed strong assumptions, A1 or A2 or A3. A3 is even stronger than A2. And the first position is to relax these assumptions. And just to avoid, because assumption about convergence, continuity in Hilbert norm is a very strong convergence. Another question is to consider continuous time problem, which only there was for a finite state space case. This was the paper of Conforrola, which had a partial result. And then a completely open problem, which I mentioned about risk sensitive. This is multiplicative cost function. We have with such a degenerate observation. So just let me say that, of course, if I assume that my operator H is in a certain set is 1-to-1, and this set is recurrent, so then I have no problem to solve ergodicity. But generally, we have to think about like in process which takes values in R, and this H is, for example, H of X is X square function. So then, if we do not observe exactly initial state of the process, we just know the law. Then we have a problem. So that's all what I will say, and thank you. Muchas gracias.
Questions? What's completely unclear for me is
Well, this was the reason. Well, it came from not only because this is hard to solve, but the motivation came from mathematics of finance. Because the heuristic is such that here in mathematics of finance, we introduce here constant gamma, which is negative. This is so-called a risk factor. And in mathematics of finance, historical results concern such so-called Markov's theory, considered the case when economists had to do the following two things. First of all, they had to maximize, they wanted to maximize expected value of the portfolio growth, and on the other hand, they wanted to minimize risk model as a variance. And here, if we have a gamma here, and if we consider this multiplicative cost function for gamma small to 0, can be written that we can expand along gamma, and we shall see that our maximization problem will be such that we maximize expected value of the growth of portfolio minus with certain gamma variance and the other. But the first is that this two functional problem, which is typical in economy, in mathematics of finance, is with two functional is replaced by one functional. Because usually we have a two criteria model, we have a problem to solve. What is the sense of solution if we have two criteria? But if we two criteria replaced by a one criterion with a certain weight, this weight comes from this gamma, so we come to this multiplicative cost function. And of course, but then our theory starts to be much, much harder. And as I mentioned, in particular, if you have a partial observation case like the one I studied here, I don't know how to formulate. If I have an additive noise, so there is a result, and we know how to handle the case. Yes.
The observed quantity,
yes.
So for this case, we have to filter what is the analog for this multiplicative case.
Well, it was this multiplicative case, of course, instead of ergodicity of this, we are studying so-called anormalized measure. I don't want to say filtering process, because this is a normalized measure-valued process, which we normalize. And of course, the explanation is for this process is so because we consider this is conditional expectation, in a sense in which is this xn plus multiplied by certain function that comes from this cost function. So this is much more complicated. But generally, to study this case, we would like to Markovianize the problem. We would like to find a Markov process. And we can find here a Markov process in the case when we have this additive noise. When we have this separation, we can use the reference probability method. If we don't have this, and in my case with this degenerate observation, we don't have this. And then we even don't know how to attack, in a sense, how to define this Markov measure-valued Markov process, which we can study, the behavior of which we can study, and hope that the optimal control will be a function. We can look for a Bellman equation and so on.